Hello viewers, in previous lecture we have discussed the characteristics of gaseous phase, the gas laws, Boyle's law, Charles' law, Avogadro's law, Dalton's law of partial pressure, Graham's law of diffusion and their application in daily life, and the ideal gas equation and their values of ideal gas constant. In this lecture, we are going to discuss the assumptions of kinetic gas theory, and then we are going to derivate the kinetic gas equation. The kinetic theory of gas was first proposed by Daniel Bernoulli, then elaborated by Clausius, Maxwell and Boltzmann. Now, let us start the assumptions of kinetic theory of gases. A gas consists of a large number of tiny particles called molecules, which are identical and very small in size. So, the volume occupied by a molecule is negligible in comparison to the total volume of the gas. Next assumption is the molecules are spherical and perfectly elastic. It means there is no attractive forces exist between them. The molecules are in state of rapid, random, straight line motion, colliding with each other and with the wall of the container, and the collisions are perfectly elastic. It means no change of energy during this collision. See, you can see in this slide these molecules are in random motion and colliding with each other and colliding at the wall of the container also. Next assumption is due to their motion, these molecules will exert pressure on the wall of the container. So, the pressure exerted by the container is only due to the collision at the wall of the container. Next assumption is the absolute temperature of gas is directly proportional to the kinetic energy of all the molecules. If we increase the temperature, the kinetic energy of the gas molecules increases. Now, let us derive the kinetic gas equation. Let us consider a cubical vessel of edge length L centimeter filled with certain quantity of gas. Consider that the total number of molecule in vessel is N, that is capital N, and the mass of each molecule of the gas is m. The velocity of molecule V can be resolved into three components along x, y and z direction. So, it can be shown as Vx in x direction, Vy in y direction and Vz in z direction. So, the mean square velocity is equal V square is equal Vx square plus Vy square plus Vz square here. Now, let us discuss the change in moment. As the face A is perpendicular to the x axis, it is visible here, hence the molecules moving along x axis will collide with the face A1 here. Like this molecule is colliding on face A1. Now, before collision, the momentum of molecule is mvx. See here, the momentum before collision is mvx, and after collision when it rebound, the change in momentum is minus mvx. So, the total change in momentum per molecule per collision on face A along x direction is 2 mvx. Before the molecule can strike the same phase again. It must travel to the opposite phase A2. This is phase A2, collide with it and rebound and return. In this case, the molecule travel a distance of 2L. The change in momentum now we can calculate. So, the change of momentum per second on phase A, which is on direction x, that is 2 mvx into Vx by L. So, it will be 2 mvx square by L here. Similarly, along y direction and z direction, the change of momentum per molecule per second is given as, on y direction it is 2 mvy square by L, and on z direction it is 2 mvz square by L. Now, we can calculate the total change in momentum per molecule per second on all 6 faces of the cube. So, on adding all these, total change in momentum on all 6 faces of the cube, we get 2 mvx square by L plus 2 mvy square by L plus 2 mvz square by L. So, now we will take 2 m by L common here. So, now the equation is 2 m by L into Vx square plus Vy square plus Vz square. As I told you before that mean square velocity, that is V square, it is Vx square plus Vy square plus Vz square. So, now we can put V square in place of this. So, now the equation is 2 m by L into V square. So, now we will calculate the total change in momentum for n number of molecules. So, now the equation will be 2 mn by L into V square. M is the mass here, n is the number of moles, V square is the mean square velocity and L is the distance. Now, we will check the pressure exerted on the wall. For this, as we know, the Newton's law of motion is force is equal rate of change of momentum. So, the pressure exerted on the wall of the container will be pressure is equal force by area. So, in place of force we will put 2 mn L by V square and A is the area here. For the cube, the area is 6L square because a cube has 6 sides. So, for this the area is 6L square. Now, we will put this value here. So, the equation will be P is equal 2 mn by 6L square into L into V square. So, that is equal 6L cube it will. So, we can write it like 6V. So, the equation will be 1 by 3 into mn by V into V square. So, finally, we get the equation, it is PV is equal 1 by 3 mn V square. This equation is known as the kinetic gas equation, and this equation is applicable for ideal gas only. So, PV is equal 1 by 3 mn V square. P is pressure exerted by the gas here, V is the volume of the gas, m is average mass of each molecule, n is total number of molecules, and finally V square. This is the mean square velocity of the gas. Now, we will do the comparative study between ideal gas and real gas. An ideal gas obeys Boyle's law and Charles' law strictly at all temperature and pressure range. It means the ideal gas obeys ideal gas equation, that is PV is equal RT. And many gases do not obey Boyle's law and Charles' law at all temperature and pressure. So, these gases are non-ideal gases. These are nearly all gases which do not follow Boyle's law and Charles' law. They deviate from the ideal behavior of gases. So, these gases are known as real gases or non-ideal gases. Now, we can discuss a very convenient method of showing the deviation for real gas is in terms of compressibility factor. Compressibility factor is defined as the product of pressure and volume of a gas divided by the product of temperature of the gas and the gas constant. Compressibility factor is represented by Z, and Z is equal PV by nRT. For ideal gas, the value of compressibility factor is always unity, and for real gas, the compressibility factor always deviate from unity. It may be greater than 1 or may be less than 1, and this extent of deviation directly depends upon the temperature and pressure. As you can see here in this graph, this is for deviation for real gases. This curve shows clearly that the real gases deviate from ideal character. As you can see here, the value of Z is not unity, it is only for ideal gas here, and a maximum deviation is seen or observed here at lower temperature and high pressure. You can see in this graph here, these are real gases and showing maximum deviation here at high temperature and at low pressure. The permanent gases like air, hydrogen, nitrogen show small deviation because of their small mass, but deviation increases at high pressure and low temperature. The gases like carbon dioxide, NO2 and ammonia, sulfur dioxide and C2H4, these gases show the large deviation from Boyle's law. Now, let us do the comparative study. So, the ideal gases strictly follow Boyle's law and Charles' law under all conditions of temperature and pressure, while real gases, they do not follow Boyle's and Charles' law strictly, but they follow these rules only at low pressure and high temperature. In ideal gas, there is no attractive forces between the gas molecule, while in real gases, the attractive forces exist between the gas molecule. The molecular collision in ideal gas is perfectly elastic, while in case of real gases, the molecular collision in gas is non-elastic. There is some change of energy. The actual volume of the molecule in gas is negligible, while in case of real gas, the volume of a molecule in gas is appreciable. That is why ideal gases follow ideal gas equation and kinetic gas equation, while real gases, they do not conform the assumptions of kinetic gas equation. In reality, there is no existence of ideal gas, while in reality majorly main gases are real gases like hydrogen, nitrogen, carbon dioxide, ammonia, these are real gases. The cooling effect is not expected during expansion. When we expand the ideal gas, there is no thermal effect is observed, while in case of real gases, the cooling effect is seen during expansion. This is Joule-Thomson effect. When we expand gas, the temperature decreases. So, this is the comparison between ideal gas and real gas. So, in this lecture, we have discussed the assumptions of kinetic gas theory, and then we derive the kinetic gas equation, that was PV is equal 1 by 3 mn V square. Here P stands for pressure exerted by the gas, V is volume of the gas, m is average mass of each molecule, n is number of molecules, V square is mean square velocity of the gas. Then we did the comparative study between the ideal gas and real gas. As I told you that for ideal gas, the value of compressibility factor is unity, while for real gas it is greater than 1 or less than 1. In next lecture, we will discuss the reasons of deviation of real gases, and then we will derive the van der Waals equation.